Hello, everyone. So we just got some major developments on 3I Atlas, and what we're seeing in these latest observations is genuinely remarkable. The Hubble Space Telescope captured new images in late December 2025, right around New Year's Eve, and what they reveal is unlike anything we've observed before. For the past 2 months, ever since this interstellar visitor made its closest approach to the Sun, something extraordinary has been happening. This object has developed what we call an anti-tail, a massive jet of material pointing directly toward the Sun, not away from it. And we're talking hundreds of thousands of kilometers in length. Now, before we go any further, if you want to follow this investigation as it develops, consider subscribing. This is the kind of mystery that unfolds over months, and the implications of what we're finding could reshape how we think about objects traveling between the stars. So, let's discuss what makes this so unusual. Comets are supposed to have tails that stream away from the Sun. That's basic physics. Solar radiation and the solar wind push material outward. It's what we've observed on every comet for hundreds of years. But 3I Atlas is doing the opposite. It's projecting material back toward our star. And here's the thing, 17 separate Hubble images from late 2025 confirm this isn't some optical illusion or viewing angle artifact. This is real. This is actually happening. Now, here's where the physics gets interesting. Earlier analysis showed that dust particles around 10 microns in size can be carried along by outflowing gas. These tiny grains get accelerated to impressive speeds, hundreds of meters per second, and they can travel enormous distances before sunlight eventually slows them down through radiation pressure. But here's the crucial detail that sets up our entire mystery. Dust and gas behave very differently once they leave the comet's surface. Dust particles are pushed back primarily by sunlight itself. Gas molecules, on the other hand, are pushed back mainly by the solar wind, that constant stream of charged particles flowing outward from the Sun at speeds around 400 kilometers per second. These are two completely different mechanisms, and they act over very different distance scales. As gas flows away from the nucleus, its density drops rapidly with distance. This isn't linear, it's inverse square. The farther the gas travels, the thinner it becomes, and the more vulnerable it is to being swept away by the solar wind. This is standard cometary physics, observed across countless objects over decades of study. Let's look closer at the data from 3I Atlas. Measurements suggest this object was losing mass at a rate of hundreds of kilograms per second. Near perihelion, when solar heating was most intense, this rate may have increased by a factor of several. We're talking about a sustained outpouring of material, day after day. If we assume the gas outflow after perihelion reached about 500 kilograms per second, and the gas velocity was around 200 meters per second, typical for gas sublimating from carbon dioxide ice at about 200 Kelvin. Then we can calculate where the solar wind should stop this outflow. The math is straightforward but revealing. The solar wind should halt and sweep away the gas at approximately 5,000 kilometers from the nucleus. So, what does this actually mean? It means that if 3I Atlas is behaving like a natural comet, its glowing gas halo should extend only about 5,000 kilometers from the central nucleus. Beyond that radius, the solar wind should be too strong, and the flow should be pushed away from the Sun, forming the standard cometary tail. This is textbook behavior. And here's where observation meets prediction. Images from the Hubble Space Telescope, 17 separate observations taken in late 2025, show that the glowing gas halo is indeed about 5,000 kilometers across. The theory matches reality perfectly. Beyond that point, the solar wind picks up the gas and carries it away from the Sun, forming an ordinary cometary tail. But the dust keeps going. Those larger grains, bigger than about 10 microns, continue streaming toward the Sun, forming that massive anti-tail that stretches up to approximately 100,000 kilometers, 20 times farther than the gas should be able to reach. This contradicts what we previously thought about how tightly coupled dust and gas remain as they leave a comet. So we arrive at a testable prediction. If 3I Atlas is truly a natural comet, then the anti-tail at large distances should contain almost no gas. It should be purely dust, tiny grains reflecting sunlight, but with no accompanying glow from excited gas molecules. This is clean, observable, falsifiable. Building on this, astronomers now have a straightforward test. Search along the axis of the anti-tail for a gas tracer like carbon dioxide or carbon monoxide. Compare the distribution of that gas signature to the sunlight scattered by dust. If the gas stops at 5,000 kilometers and only dust continues beyond, the natural comet hypothesis holds. If significant gas is found far out along the anti-tail, then something else must be accelerating it. Something capable of giving gas much higher speeds than natural sublimation can provide. And that's where this story takes a turn into territory that makes some scientists deeply uncomfortable, while others find it thrilling. Let's dig into the numbers, because this is where the mystery becomes quantifiable. As we established, the glowing gas halo around 3I Atlas extends about 5,000 kilometers from the nucleus, exactly where theory predicts the solar wind should overpower natural gas outflow. But that anti-tail reaches 100,000 kilometers. We need to understand what it would take to push gas that far. The key lies in exhaust velocity. When gas sublimates naturally from a comet's surface, heated by the Sun, it leaves at speeds determined purely by temperature. For carbon dioxide ice at around 200 Kelvin, that's approximately 200 meters per second. This is thermal motion, molecules escaping into space. There's no additional acceleration, no engine, just heat converting ice to gas. This natural velocity allows gas to travel about 5,000 kilometers before being stopped and swept away. Now, let's perform a thought experiment. What if something were actively accelerating that gas to much higher speeds? Let's look closer at the data and see what different exhaust velocities would mean. Consider a chemical rocket. A typical chemical rocket ejects material at around 5 kilometers per second, roughly 25 times faster than natural sublimation. If gas were being expelled at that speed, it would have 25 times more momentum. The math tells us that gas from a chemical rocket could reach approximately 25,000 kilometers. That's 5 times farther than natural outgassing, but still only 1/4 of the way to the observed anti-tail length. But what about more advanced propulsion? Here's where things get truly interesting. An ion engine, the kind used on deep space probes like Dawn and Bepi Colombo, accelerates propellant using electric fields. These engines eject matter at around 90 kilometers per second, roughly 450 times faster than natural sublimation. If gas were being expelled by an ion engine at 90 kilometers per second, it could travel approximately 100,000 kilometers before the solar wind stops it. 100,000 kilometers. Exactly matching the full observed length of the anti-tail. This contradicts what we previously thought we were looking at. When the anti-tail was first observed, the natural assumption was dust grains with perhaps some residual gas close to the nucleus. The idea that gas might be present throughout the entire structure wasn't seriously considered because there's no natural mechanism to get it there. Thermal sublimation simply cannot provide the necessary velocity. So, what does this actually mean? It presents us with two possibilities. The first is that the anti-tail at large distances contains only dust with no significant gas, and natural cometary processes explain everything. The second possibility, and this is where we enter speculative territory, is that there is gas at large distances and something artificial is accelerating it to those extreme velocities. Testing this hypothesis is straightforward. Astronomers can use spectroscopy to search along the axis of the anti-tail for molecular signatures. Carbon dioxide and carbon monoxide absorb and emit light at very specific wavelengths. Large ground-based observatories or space telescopes like James Webb could map the distribution of gas along the entire length of the anti-tail. The test is simple. Point the telescope along the anti-tail at various distances. Look for gas signatures. If you find significant emissions at 10,000, 50,000, or 100,000 kilometers, then you've falsified the natural comet hypothesis. Something is giving that gas enormous velocities that natural processes cannot explain. Building on this, we need to consider what we're actually proposing. An ion engine capable of producing 90 kilometer per second exhaust velocity isn't something that occurs in nature. It requires electricity, magnetic fields, acceleration grids, and a power source. We're talking about technology, not geology. We're talking about engineering, not natural processes. When we discuss the possibility of artificial technology in connection with an astronomical object, we're not making claims. We're following the data and asking what different observations would imply. This is how science works. You make predictions, then you test them. If you find gas at 100,000 kilometers, the natural comet hypothesis has a serious problem. Let me throw out a question to all of you watching. Given that we have the capability to perform this test with existing telescopes, why do you think these observations haven't been prioritized? Is it because telescope time is precious? Or is there perhaps some reluctance to pursue a line of inquiry that could yield uncomfortable answers? What would you do if you controlled the observation schedule? The beautiful thing about this mystery is that it's entirely empirical. Either there's gas out there at large distances, or there isn't. Either it has the velocity profile consistent with ion propulsion, or it doesn't. These are yes or no questions, and the telescopes can answer them definitively. Science advances through observation, not through forcing nature into preconceived explanations. We could look at 3I Atlas, decide it's a comet because it looks vaguely cometary, and move on. Or we could actually test the hypothesis rigorously, make measurements, and let reality tell us what it is. As we'll explore next, when we zoom in closer to the nucleus and examine the detailed structure of the jets, we find geometric patterns that raise entirely new questions. The velocity calculations we just discussed tell us what's physically possible versus what's naturally expected, but they leave open a provocative question. If gas is indeed traveling to 100,000 kilometers along the anti-tail, requiring exhaust velocities consistent with ion propulsion, what exactly would that imply? This is where we move into hypothesis territory. We're not claiming anything is true. We're exploring what different observations would mean if confirmed. Let's start with the most conservative technological scenario. Imagine that 3I Atlas contains some kind of chemical propulsion system, chambers of stored reactants that heat up as the object approaches the sun and begin producing thrust. Chemical rockets are relatively simple technology. The exhaust velocities are well understood, around 5 kilometers per second. If such a system were operating, it could explain gas reaching 25,000 kilometers. That's 5 times farther than natural sublimation. Impressive, but still short of the full anti-tail length. But here's the crucial detail. Even this conservative scenario requires extraordinary coincidences. The propellant would need to ignite at exactly the right temperature, producing thrust in exactly the right direction, maintaining that thrust for weeks. Chemical rockets don't spontaneously maintain stable burns for extended periods. They require ignition systems, fuel management, combustion chamber integrity. Could nature produce something functionally equivalent through random processes? Now let's consider the more capable scenario, the one that actually matches the observations. An ion engine with 90 km per second exhaust velocity could push gas out to the full 100,000 kilometer extent. This technology is significantly more sophisticated. Ion engines require electrical power, typically from solar panels or nuclear sources. They need magnetic fields to accelerate ionized particles. They require propellant storage, flow control, and power management systems. These aren't things that form naturally through geological processes. So, what does this actually mean if spectroscopic observations confirm gas at large distances? It means we have to seriously consider that 3I Atlas might not be entirely natural, that somewhere along the line, whether recently or in the distant past, technology was involved in its creation or modification. This is not a comfortable conclusion, but if the data demands it, we have to follow where it leads. Building on this, let's talk about what upcoming observations could reveal. The test itself is straightforward. You point a telescope equipped with a spectrograph at the anti-tail at various distances. You look for emission or absorption lines characteristic of carbon dioxide or carbon monoxide. You measure the intensity and construct a profile of gas density versus distance. If the profile shows gas only within 5,000 kilometers and nothing beyond, the natural comet hypothesis is strongly supported. The anti-tail would be confirmed as purely dust. Everything fits, and 3I Atlas goes into the books as an unusually active interstellar comet. However, if the profile shows significant gas at 10,000, 25,000, 50,000 kilometers or beyond, then we have a problem. Natural sublimation cannot explain it. We're forced to invoke something actively accelerating the gas to high velocities firmly in the regime of engineered propulsion systems. This contradicts what we previously thought about interstellar objects. When Oumuamua passed through in 2017, there was debate about whether its trajectory showed signs of non-gravitational acceleration. Some proposed it might be a light sail. The controversy died down without resolution, largely because Oumuamua was leaving by the time anyone realized how unusual it was. But 3I Atlas is different. We have 17 Hubble images from late 2025 alone, plus numerous ground-based observations. Unlike Oumuamua, we haven't missed our opportunity. The observations that could resolve this mystery are still possible. Let's look closer at the data we already have. Those Hubble images don't just show the large-scale anti-tail. When you zoom in on the region close to the nucleus, you see structure. The jet configuration is not simple. There are multiple jets, and their arrangement is geometrically precise in a way that demands explanation. Such observations could be performed using several facilities. The Very Large Telescope, Keck Observatory, or James Webb Space Telescope could all detect these signatures. These aren't hypothetical instruments. They exist now. Someone just needs to convince the Time Allocation Committee that this observation is worth pursuing. Given what we now understand, we have clear, testable predictions. The natural hypothesis predicts no gas beyond 5,000 kilometers. The chemical propulsion hypothesis predicts gas reaching about 25,000 kilometers. The ion propulsion hypothesis predicts gas throughout the full extent. 3 different scenarios, 3 different observational signatures. If you found this analysis compelling and want to see scientific content like this get more visibility, consider giving this video a like. Your engagement literally helps determine what science gets done. As we move forward, we need to examine the detailed jet configuration near the nucleus, because that's where the geometric puzzles become truly perplexing. Now we need to zoom in, shift our focus from the enormous anti-tail to the region immediately surrounding the nucleus, because this is where the geometric precision becomes genuinely difficult to explain through natural processes alone. Those 17 Hubble images from late 2025 reveal something that wasn't apparent in early observations. The jet configuration around 3I Atlas is organized in a pattern that shows remarkable symmetry. At large scales, we see that dominant anti-tail pointing back toward the Sun. But closer to the nucleus, at distances about 10 times smaller, roughly 10,000 kilometers out, 3 secondary jets become visible. One jet points away from the Sun, which is exactly what you'd expect from a natural comet. Material heated on the sunward side sublimates and flows away. Standard cometary behavior. But then there are the other 2 jets. They're separated symmetrically from the anti-solar jet by approximately plus or minus 120 degrees. Think about what that means geometrically. If you're looking down from above the rotation axis, you'd see 3 jets evenly spaced around a circle, each separated by 120 degrees. The Hubble images show precision angular spacing that matches a perfect three-fold symmetric pattern. Let's look closer at the data and ask the obvious question: how does nature produce such precise geometric arrangements? On Earth, we see symmetry in snowflakes, in crystals, in flower patterns. These arise from underlying molecular structure, from crystalline lattices, from genetic programs. Symmetry in nature typically reflects some fundamental organizing principle. For a comet, the organizing principle would be the distribution of volatile ices on the surface. As the object rotates, different patches of ice are exposed to sunlight, heat up, sublimate, and produce jets. If you happen to have three large patches of ice arranged with perfect 120-degree spacing, you'd see exactly this pattern. So, what does this actually mean? It means we need to ask about probabilities. What are the odds that natural geological processes would produce three volatile rich regions with such precise angular spacing? Geological processes are messy, random, chaotic. Impacts crater the surface irregularly. Thermal evolution creates stress fractures that don't respect geometric symmetry. Could it happen? Certainly. But how likely is it? Building on this geometric puzzle, let's discuss the temporal behavior. The Hubble observations show that the directions of the jets change over time, which is expected if the object is rotating. Analysis suggests a timescale of about 8 hours, consistent with the rotation period of the nucleus. Here's the crucial detail. Variation of the three secondary jets over 8 hours can easily be explained by natural rotation speeds and sublimation rates. An 8-hour rotation period is unremarkable. None of this is problematic for the natural comet hypothesis. But then we come back to that main anti-tail, the dominant structure that extends 10 times farther than the secondary jets. For this massive feature to maintain its existence and direction while the object rotates requires something very specific. The rotation axis of 3I Atlas must be aligned almost perfectly with the direction toward the Sun. If the axis were tilted significantly, the main jet would sweep around just like the secondary jets, and we'd see the anti-tail precess or wobble. The fact that we see a stable, persistent anti-tail means the misalignment must be extremely small. The analysis suggests just a few degrees at most. This is an extraordinary constraint. Imagine spinning a top and having its axis point at a specific object across the room to within a few degrees, not by your careful aim, but by pure chance. This contradicts what we previously thought about how interstellar objects should be oriented. These objects have been traveling through the galaxy for millions of years, tumbling through space, subjected to gravitational perturbations. There's no reason their rotation axes should have any particular alignment with our Sun. The orientation should be essentially random. So we can calculate the probability. If the rotation axis can point anywhere on a sphere with equal likelihood, what fraction corresponds to pointing within a few degrees of the Sun? The numbers work out to approximately 0.2%. That's 2 chances in 1,000. Not impossible, but definitely unlikely. We're not saying it's impossible for 3I Atlas to have this alignment by pure chance. We're saying that if you observed 1,000 interstellar objects, you'd expect to see this kind of precise alignment in maybe two of them. 3I Atlas happens to be one of the first few interstellar objects we've ever observed in detail. And so the main question arises once more. Are the symmetric triple jet pattern and the extremely unlikely geometric alignment natural consequences of cometary physics and lucky coincidence? Or do they suggest something else, some level of design, control, or technological intervention that produced these precise geometric relationships intentionally? Given what we now understand, we're faced with a scenario where multiple low-probability features have all appeared together in the same object. The symmetric 120-degree spacing, the near-perfect alignment of the rotation axis, the extended anti-tail. Any one of these features might be dismissed as an interesting anomaly. All of them together start to look like a pattern. In statistics, if you need several unlikely things to all happen together, you multiply their individual probabilities. A 0.2% chance alignment is already uncommon. If the symmetric jet pattern also has, say, a 1% chance, you quickly arrive at scenarios where the combined probability is vanishingly small. Let me pose a question as we head into the final section. If you were tasked with building a probe to travel between star systems and you wanted it to pass as something natural, how would you do it? Would you make it look obviously artificial? Or would you disguise it, coat it with ice and rock, program it to sublimate material as it approaches the star? These aren't claims. These are questions that follow logically from the observations. Let's bring this all together and confront what we're really asking here. We started with an anti-tail that extends 100,000 kilometers toward the Sun. We calculated that natural gas outflow should stop at 5,000 kilometers. We explored what exhaust velocities would be needed to push gas to the full observed distance and found that ion propulsion matches the requirements. We examined the jet geometry and discovered precise 120-degree symmetry. We looked at the rotation axis alignment and calculated a 0.2% probability. Every step has been data-driven, quantifiable. Now we have to ask the synthesis question. Taken as a whole, what does all of this evidence tell us about the nature of 3 Atlas? Is it simply a very unusual natural comet with several improbable features all at once? Or are we looking at something that involves technology, design, artificial construction? This is not a comfortable question for mainstream astronomy, but it's the question that the data forces us to confront. As we established earlier, science advances through observation, not through protecting comfortable paradigms. For most of astronomical history, we've been able to classify objects into neat categories: stars, planets, asteroids, comets. Each category has defining characteristics. The system works beautifully for the vast majority of what we observe. And then something like 3I Atlas comes along and doesn't quite fit. The natural instinct is to force it into an existing category. It has a tail, it sublimates material, therefore it's a comet. But that approach only works if you ignore the quantitative details. The 5,000-kilometer gas limit versus the 100,000-kilometer anti-tail. The precise geometric symmetry, the 0.2% alignment probability. You can't just wave these away. Let's look closer at the data one more time and consider what different future observations could tell us. First, the spectroscopic test. If astronomers find significant carbon dioxide or carbon monoxide emissions at distances of 50,000 kilometers or beyond, that would be strong evidence that gas is being actively accelerated to high velocities. It wouldn't prove artificial technology, but it would eliminate simple, natural sublimation. Second, if those observations could measure the velocity distribution of the gas directly through Doppler shifts, that would be even more definitive. Gas naturally sublimating has a thermal velocity distribution. Gas accelerated through an ion engine would have a different distribution, narrower and centered at much higher velocity. The James Webb Space Telescope could potentially make these measurements. Third, continued monitoring of the jet geometry could reveal whether the patterns are truly stable or whether they evolve. If the 120-degree symmetry persists for months despite changing conditions, that's harder to explain naturally. If the main anti-tail maintains its alignment despite orbital mechanics, that suggests active attitude control. So, what does this actually mean for the broader question of whether we're alone? For decades, SETI has focused on radio signals. We've scanned millions of star systems and found nothing conclusive. The silence has been interpreted as evidence that we're alone or that civilizations don't last long enough to overlap. But there's another approach, looking at physical objects passing through our solar system. Not radio waves, but actual artifacts. This was part of the motivation behind scrutiny of Oumuamua. If interstellar space contains even a small population of artificial objects, occasionally one should pass close enough to be detected. Building on this, consider the engineering perspective. If you wanted to send probes to other star systems, what design would you choose? Pure metal spacecraft are resource-intensive and easily detected. But if you coated your probe with ice and rock, gave it a cometary appearance, programmed it to sublimate material while also providing thrust vectoring, you'd have something that could pass through without immediately screaming artificial. This contradicts what we previously thought about how extraterrestrial probes would look. The popular imagination pictures flying saucers, gleaming metal, obvious technology. But any civilization capable of interstellar travel would have had millions of years beyond our current state. Their engineering would be sophisticated beyond our comprehension, and their design choices would optimize for efficiency, longevity, perhaps stealth. The hypothesis that 3I Atlas might be partially or wholly artificial doesn't require it to be actively controlled at this moment. It could be a derelict, a probe that completed its mission millions of years ago, its systems still functioning enough to provide attitude control and thrust, but no longer transmitting data. It could be a passive monitor. It could be any number of things. Here's what we do know with certainty. The data shows features that are, at minimum, highly unusual. The extended anti-tail, the symmetric jet pattern, the improbable alignment. These are not in dispute. What's in dispute is the interpretation. Do these features have natural explanations we haven't thought of yet? Or do they point toward something artificial? Given what we now understand, The natural explanation requires stacking several low-probability events together. You need the geometric alignment, the symmetric jets, the extended gas distribution if it exists. That's possible, but the combined probability is low. The artificial hypothesis, by contrast, would make all these features expected consequences of design. Before anyone accuses me of claiming that 3I Atlas is definitely artificial, let me be absolutely clear. I am not making that claim. I am saying that the hypothesis is worth taking seriously, worth testing with observations, and worth discussing openly without dismissing it as fringe speculation. And this is where I want to leave you with a final thought. Science is not about maintaining consensus. It's about pursuing truth wherever it leads, even when it challenges our assumptions. The history of scientific progress is filled with moments when someone questioned the accepted framework. Continental drift, plate tectonics, heliocentrism. Every major paradigm shift started with someone asking, "What if we're wrong?" 3I Atlas might be a natural comet with very unusual features, or it might be something more. We won't know until we do the observations, and that requires resources, telescope time, and the intellectual courage to pursue answers even when we're not sure we'll like what we find. If you found this deep dive valuable, please like this video to help it reach a wider audience. The more people who understand that these are legitimate scientific inquiries, the more likely we are to see the observations funded. Your engagement matters. Where do we go from here? The spectroscopic observations need to happen. The velocity measurements need to be made. The jet geometry needs continued monitoring. And we need more objects. As our detection capabilities improve, we'll find more interstellar visitors. With a larger statistical sample, we can answer questions about what fraction shows these unusual features. The universe is vast, ancient, and full of possibilities. If technological civilizations exist elsewhere, and if they've been around for even a tiny fraction of the age of the galaxy, then the interstellar medium should contain some trace. We've only just started looking carefully at objects passing through. What we find may reshape our understanding of our place in the cosmos. 3I Atlas is out there right now, continuing its journey. The opportunity won't last forever. In a few years, it will be too faint, too distant. If we want answers, we need those observations soon. The data is within reach. The questions are clear. All that's needed is the will to pursue them. Thank you for joining me on this deep dive. Keep looking up, keep asking questions, and keep demanding that science follow the data wherever it leads.